Okay, so in this series of videos, we're going to continue to extend our treatment of gravitation and central forces. And in this video in particular, we're going to be taking a look at the gravitational potential and potential energy in a general central field. Okay, so we'll start by taking a look at the gravitational potential. And we'll start first by thinking about the potential energy. So that's going to come from calculating the work. So let's say I've got, and I'm trying to do this in 3D here, I've got some fairly largish mass here. Well, it doesn't have to be large, but we'll see. And we'll imagine that I move it from here to there. And I can move it, say, along this path right here. That looks as good as any to me. So at this point right here, it would be feeling a force back like so. And we will start from position R1 and end up over there at position R2. Okay. So we'll go ahead and calculate the work done by the gravitational force. So along some differential of this motion, we were currently located at R. We're going to displace over some distance dr like so. We can project that down, and the radial component here will be dr without the vector. It would be equal to f dotted with dr. So it'll be equal to minus gm over r squared times r hat. So this much is the force, and remember it's pointing in and r hat points out, thus the minus sign. And we'll dot that with our dr. So substituting in, our dr is equal to is just equal to r hat times the scalar dr. So r hat dot r hat is just unity, it just leaves behind the scalar dr, and there we go. So the total work done will be equal to integral from r1 to r2 of our minus, well, we can pull some stuff out of the minus the integral. Let's do that. We can pull out a minus gm. We'll be left with an integral r1 to r2 dr over r squared, and that will give us minus 1 over r, but we got a minus in front, so it leaves us a little plus. So gm times 1 over r2 minus 1 over r1. So remember, the change in the potential energy will be equal to the negative of the work. So the change in the potential energy would pick up a minus sign, so minus gm times 1 over r2 minus 1 over r1. Now, any function that we can dream up such that the difference at r1 and r2 is that will work just fine. Now, as a practical matter, it's going to be the same, pretty much the same function, just with a whole bunch of different choices of constants. And I would submit that the calculus of the situation makes it really convenient to choose. So this is by convention, but everybody does this for good math reasons. We choose to set the potential at infinite separation, potential energy, sorry, at infinite separation to 0. So if we make that choice, so we have made a particular choice, we could have made others. If we make that particular choice, then we can write v of r is minus gm over r. Now, we could have made other choices, but really they would just amount to adding a constant. The constants would cancel, oh yay, but it would make the math a lot harder, so this is the conventional choice. Now, I should point out that before we go on much further with gravity, classically here we're faced with a conundrum. The conundrum is the problem of action at a distance. So this is a little side note here. What this means is that in Newton's model of gravity, interactions are instantaneous over all distance scales. It was thought, I mean, people weren't totally happy with that, but it was thought necessary in order to respect the simultaneity that Newton's third law requires, because it says that all interactions are mutual and simultaneous. Now, this leads to a problem in light of special relativity. As you know, in special relativity, information can't travel faster than the speed of light. There are things that can, but they can't affect things until the information catches up. Also, the universe is allowed to expand faster than the speed of light. That's okay too, because that's space itself. So here's the thing. So Newton's view, if we look at the Earth orbiting the Sun, let's say, greatly not to scale here. And sorry, I gotta do that again. All right, so let's try doing that again a little better. So so let's say this is the Sun. And this is the Earth orbiting the Sun. Just drawing a little bit of the orbit. So the distinction is that according to Newton, so we'll make Newton green, or sorry, blue here. According to Newton, the Earth is falling to where the Sun is. Special relativity, though, requires that the Earth not fall to where the Sun is, but to where the Sun was 8 minutes ago. That's going to be a little different. Barely, but it is measurable. Now, to get out of this pickle, what we've done is we've developed the idea of the gravitational field. Now, it turns out general relativity will tell us that in this particular case, space itself is the field. For all other forces, the field is a property of space. The one big thing we've learned in the 20th century is that space-time is a thing, but we are working very hard to try to describe the thing. So what we say is the Sun influences the gravitational field. The changes in the gravitational field propagate out at the speed of light, and the Earth then interacts with the field right there. So Newton's third law is respected locally because the interactions with the field, and so the field acts on the Earth and the Earth acts on the field, and that's all instantaneous. And then we can let changes propagate through the field at the speed of light in the case of gravity and the electromagnetic force, other speeds for other forces. And then other objects will interact with that field as it updates later, and that will also respect the simultaneity that Newton's third law requires, because it will be a simultaneous interaction between that object and the field right exactly where it is. So by making all of our interactions occur locally with that property of space called the field, Newton's third law is still respected. Now, quantum mechanics takes this idea even a little further. There are different names for it. I learned it as the second quantization, but in any event, quantum mechanics goes further to say that particles are excitations of fields. And all particles, so electron could be an excitation of an electron field, over simplifying things there. And so it goes to say that we can also model a interaction as an exchange of particles. Let's keep that red for the moment. So for instance, say if it was the electromagnetic field, you might have some electron, like so, interacting with some other electron, and you can see they've changed their momenta. And they do this by exchanging a photon with each other. Once again, Newton's third law is still respected because the interaction is at, now the jargon would be the vertex, but right again would be local, so Newton's third law is respected there, and it's respected there. So this is a natural way that we can give momentum to the field, and like we say, we would say that the photon represents an excitation in the field. All right, so that's our side point here. What we're going to do now is work on constructing the gravitational field. Now, like I say, in general relativity, we will come to the conclusion that space-time itself is the gravitational field. In this classical view, we're not going to go that far. We're going to treat it as a property at a location in space, just like any other just like any other field, such as the magnetic field or the electric field or something like that. And this is okay as long as you're not standing next to a black hole or a neutron star. You're not going at major fractions of the speed of light, etc., etc. This is what gets called the weak field limit. You can treat it this way. But that's what we're working towards building, is the weak field limit of it. So I'm just putting that out there so that if you go on to take general relativity, you'll realize that this was a limit of our current understanding. So that end, let's go ahead and construct the gravitational potential. We can do this in analogy to constructing the electric potential in your 200 level E&M courses. We imagine some small mass, and we need it to be small so that it doesn't disturb the gravitational field, doesn't disturb the collection of the other masses in the area significantly. And we'll then just define the gravitational potential phi to be the limit as this test mass, so it doesn't even actually have to exist. We can just make it a mathematical construct. As that mass goes to zero, it'll be the potential energy of the system with that test mass divided out. So once we've done that, then if we choose to place a real mass at some location later, the potential energy we'd have due to placing it at, say, XYZ would be the mass of the thing times the potential. So the potential energy is the potential. Two different things, very similar term, again, just like with electricity and magnetism. And this would be due to the other players in the system. All right, so we can follow that logic out. So let's say I just have a single point mass right there. And I want to know the potential at this point in space due to that point mass. Let's say it's a distance r away. Well, we could go ahead and imagine putting some hypothetical made up, doesn't actually exist test mass right there. So this is just a test mass. It doesn't really even exist. It's just a figment of our imagination. But we could go ahead and say that the potential energy of that system would be minus GMM over R. All right. Actually, let's make that M green. So then the gravitational potential, phi, would be the limit as my M goes to 0 of minus G M over R, all divided by M. Well, that's going to be a really straightforward limit to take because those M's are going to cancel. And so I'm just left with a constant. I get that the potential for a point mass is minus GM over R. Okay. So now let's say I have more than one mass. So this is the origin of my system here. Let's put, say, M1 here, M2 there, M3 over here. Let's say that's my point of interest right there. So my point of interest would be located at R. That would be R1, R2, R3, like so. All right, so in that case, the potential due to multiple masses would be, well, we can pull out a minus and a G for what it's worth. Then we can just say sum over our masses, Mi over R minus Ri. So that would correspond R minus Ri. If we subtract that, that would be what I would add to this mass, say, to get to here. So this would be R minus R1. This would be R minus R2. That would be R minus R3, and so forth. Now we're just going to take the magnitude. So interpret that as this distance for the first term, then that one, and so forth. All right. So now that we've computed the potential, now let's work on getting the gravitational field intensity. All right, so just a real quick reminder of what mathematical fields are. Let's say you go and look at some temperature map of the state. You can pick a point on the map and it would return a temperature. This would be what we call a scalar field. So attached to each location in space is a scalar number, in this case the temperature. A vector field is the same idea, except vectors. So in this case here, something like that, we could go and look at the map, and you would see a whole bunch of vectors pointing in different directions, like so. And this would be a winds aloft map, let's say. So it says, I pick a particular location, like say here, and it says the wind is blowing that way, that fast. But it's only attached to this point here. Okay. We've already, our gravitational potential is already an example of a scalar field. So now let's go ahead and find our gravitational field intensity. So we'll let G be defined to be the limit as our test mass goes to 0 of the gravitational force exerted on our test mass with the test mass itself divided out. Then again, we want the test mass to be so small as to not move around the other masses, at least over the time scale we care about. So once we have that, then if later I choose to put a mass at some location, the force that that mass would feel would be its mass times the gravitational field intensity at that location. So for instance, if this is the sun right here, if I'm here, the gravitational field intensity would be rather large. If I'm out there, it'll be rather weak. And that would just tell me if I put a mass here, it'll feel a gravitational force this way. If I have doubled the mass, it'll be double the force, and so forth. Then say if I was over here, it would be, as long as I'm the same distance away, the intensity would be the same. Like so. So we are interpreting this much the same way, this little g. Interpret this much the same way that we interpret the, say, the electric field vector in electricity and magnetism. Just like there, you would interpret it as the force felt per unit charge if you chose to put a charge at some location. Here, the mass is the gravitational charge, if you will. And so again, it's telling us the force per charge. We put some mass at that location, and away we go. This does get at a little point about mass. The m in F equals ma and the m in F equals mg are technically different m's. The m in ma is what we call the inertial mass, and it measures how hard it is to change the velocity of something. The m in F equals mg is what we call the gravitational mass, and that's effectively the gravitational charge. It dictates the strength of the gravitational interaction. Now with the electric force, those are two totally different numbers. You give them two totally different symbols, m and q. Very careful experiments have been done, and at the part per billion level, we know that the gravitational and inertial masses are equal. They may be more equal than that, but that is just as accurate as the best experiment has been done. So we know it's at least that good. Might be better. So what we do is we just go ahead and tacitly assume the equality and give both of them the symbol m, and we cancel them willy-nilly. But technically we should be a little more careful because of the different roles. Now Einstein took that equivalence, and that was part of something he pushed on to eventually build special relativity. Or sorry, general relativity. All right, Now, we remember from before with potential energy, the force anything feels is equal to the negative gradient of the potential energy. Now, I could just as easily divide this through by m, and then I could take the limit of that as m goes to 0. And when I do, I'll have F over m and take the limit. That will give me the gravitational field intensity. And then V over m is just going to be phi. So then since it's a scalar, I can pull it into the gradient. And I get that the gravitational field intensity is equal to the negative of the gradient of the gravitational potential. Now, normally we don't really bother building up all this machinery in the introductory level because frankly most of the time it isn't really that helpful. It's a lot more helpful with the electric force because you have both positive and negative charges. But since the charge strength, if you will, is the same both for is always positive in the case of gravity, since the charge is always positive. It's not as helpful. There are specialized situations where it is helpful. For instance, if you're calculating satellite trajectories, say, it's very helpful. And so this formalism here, developing the potential and the field, can be very helpful for doing stuff like that. Another thing where it's helpful, though, is, say, we can do things like revisit the Shell Theorem and we'll find that it's easier to do because we can treat, since phi is a scalar, the math is a lot easier. So you remember the Shell Theorem from a couple of videos ago. So I'm just redrawing the essential bits of it right here. So that's O, P, that's Q there. This much here is our angle d theta, and this angle here is theta. Okay, and then continuing onward, this distance here is r, sorry, capital R. This distance here is lowercase r, and then to complete it out, that distance there is s. Okay, so with all of that we've developed here, we can say d phi is equal to minus g dm over s. And we already worked out what our differential mass was, so I'm just going to put that in. So it's minus g times 2 pi sigma r, that's a sigma, 2 pi sigma r squared sine theta d theta over s. And we still have to invoke the law of cosines. So they'll say that s squared is equal to r squared plus r squared minus 2rr cos theta. And then since we got sine theta d theta just screaming at us there, we differentiate both sides. So we do a formal derivative. We get 2s ds here, constant, constant. We'll be left with a derivative of cosines minus the sine, minus minus is a plus. We'll have 2rr sine theta d theta, cancel, cancel. And so we have here a sine theta d theta over s. So let's just build that. Sine theta d theta over s. We work out to be ds over rr. Okay, so putting that in, we get that phi is equal to minus g times 2 pi sigma r over r, integral minus little r minus big R to little r plus big R ds. And that's a really easy integral to evaluate. So minus g 2 pi sigma r over r times r plus r minus r minus r. Okie dokie. So look in here, the little r's cancel, the big r's stay behind, and we'll have 2 big R, so this gives us minus g times 4 pi r squared sigma over r. And we look at this and say, zounds, that is the mass of the shell. So we're left with minus gm over r. The beauty of this is you can see we still had to invoke the law of cosines, we only had to do it once. We didn't have to do it twice. That angle phi that we had over here, you notice I didn't even bother drawing it in. I guess I could draw it in now for what it's worth. There, phi. But it really doesn't do anything for us. We needed it in order to take the components of the force, or alternatively the field if we wanted. But there you go. So we've got that's in inverse squared law right there. And if we wanted to get the but in case that wasn't immediately obvious, let's go ahead and take the negative gradient of the field. So quick reminder, since we're working in 3D, spherical coordinates are our winner here. So in spherical coordinates, the gradient is expressed as r hat partial r plus theta hat times 1 over r partial theta plus phi hat times 1 over r sine theta partial phi. So we'll go ahead and take our gradient here to get the gravitational field intensity. So G is minus the grad of phi. Right. So, yeah. So G is minus the gradient of phi. So that will be minus times, so we'll have an r hat partial r of minus gm over r, and then the other terms just wind up being 0 because we're taking derivatives with respect to theta and phi with something that only depends on r. So that term will go to 0, that term will go to 0. That's why we love spherical coordinates when the symmetry is appropriate. So this minus gives me a plus, but then when I differentiate, I'm going to bring down another minus, so I'm left still at a minus. I get minus gm over r squared, r hat. Okay. And the force is equal, remember, to mg, so it's minus gm over r squared, r hat, just as before, but instead of it taking me 20 minutes and doing an enormous tour de force with the law of cosines, and doing some ugly integrals, it winds up being a lot cleaner. And so that was for outside the shell. If we want to do inside the shell, that's just like before too. It's the same integral, just with the different limits of integration that you have shown. 2 pi r over r integrate this from r minus r to r plus r. So we just swap the big and the little r. So this becomes minus g 2 pi sigma r over r times r plus r minus r minus r. In this case, it's the little r's that end up, I'm sorry, the big r's that end up canceling. And I get 2 little r. But the 2 little r is going to wind up canceling against that r there and just eventually leave me, so we got 2 there after all that. So we're just left with minus g times 4 pi sigma. And we have one r already, but to just make it a little more informative, we'll multiply and divide it by r so I can still get my big M. So the potential is minus gm over r, but the key thing is it's a constant. It's also exactly what you expect because that would be the potential at the boundary of the sphere. So the gravitational field intensity is minus grad phi, which is 0 because we're differentiating a constant. So the gravitational force is 0 as before. All right, so that's a lot easier, and that's why we like, sometimes even when gravity gets a little messy, bringing in the potentials and using that machinery can be super helpful. For instance, let's say that you happen to be near some massive disk. We'll say so there's our massive disk, and there's its symmetry axis like so. Here's our point of interest here. We'll put a small mass m there, and we want to find the force on it due to the disk. So we'll say that the disk is located, the mass is located z above the disk. We'll say that the radius of the disk is a. Okay. So the trick here is we'll just look at a washer of radius x, and so that will make this width right there dx. So that we can do. We don't have to take any components. I'm just making life a little easier on myself. This is all the same distance, little r, away. So the differential contribution to the potential, there will be minus g dm over r. There'll be minus g, so I need this area here times it by the surface area density, so that will be 2 pi sigma x. So 2 pi x is the circumference. We times it by the differential thickness dx. And then we're going to divide that by r. Now r depends on x, so we're not done yet. So we get that this is minus g 2 pi sigma. Those are all constant there. I'll have x over root x squared plus z squared dx. Okay, now we're good to integrate. So the potential at an elevation z above the disk will be minus g times pi sigma. I'm going to put the 2 inside for my own nefarious reasons. G pi sigma integral 0 to a of 2x dx over the root x squared plus z squared. And I think you can see where we're going with this. This is solved by some trig substitution or other, but frankly, this is just the standard form, and I looked it up in a table. So the answer is minus g times 2 pi sigma root x squared plus z squared. Oh, I'm sorry. You can just do this by u substitution. My bad. Evaluate from 0 to a. All right. So we go ahead and do that evaluation. We get minus g 2 pi. Now my sigma is the mass of the whole thing over the area of the whole thing, pi a squared, so that cancels the pi's. Then this will be root a squared plus z squared minus just plain good old z. All right, that is about as far as we can take our phi. But you gotta admit that so far this has been a lot easier than trying to calculate g directly. So now we're going to calculate g at z and say that's equal to negative the grad of phi. All right, so minus sign, and we have a minus there, gives me a plus. So I have 2gm over a squared. And then let's see, when I differentiate this, I am going to get z over root a squared plus z squared minus 1. So then if I want the gravitational force, I can just say the gravitational force, well, the z component of it anyway, but if we're on the axis by symmetry, it can only be the z component, is equal to mg sub z. So there you go. It's 2gmm over a squared times z over root a squared plus z squared minus 1. Oh, I'm sorry, I skipped a step there. I really shouldn't, because I need to find g sub z. So just give me enough room here to do that. So for the reason I was finding g sub z was I says the gradient of phi, but I didn't really point out that I need to work in cylindrical coordinates here, and the only coordinate that counts is going to be minus a z hat partial z of the stuff we had before. Okay. And we're choosing cylindrical coordinates because we have a cylindrical symmetry. Always choose your coordinate system to match the symmetry of the problem. Okay, so with that as set up, let's now go and look at the more general case of the potential energy in a general central field. So the only requirement I'm putting on this is that the field is central. Not all fields are. The magnetic field isn't, for instance, but the electric field is, so that's good. Gravity is, that's good. So again, this means that I can write my force as some F equals some F of R, so that's the scalar force function, times R hat. If it returns negatives, it's attractive. If it returns positives, it's repulsive. So we want to see first, is a general central field conservative? So to do that, we would need to take the curl of F and see if it's 0. So we're going to do this in spherical coordinates. That's the natural choice. So it'll be 1 over r squared sine theta. So then we have r hat, theta hat r, phi hat r, sine phi. Yeah, it's not as easy a mnemonic when it's in spherical coordinates, but see the appendix in the back of your book. Partial r, partial theta, partial phi. Then we have f sub r r times f sub theta and r times f sub phi, whoops, r times f sub phi sine theta. And we do the same fakey determinant that we've done before. Now, if it's a central force, equals, well, I'm just going to steal all that. Oops. Let's try that again. I'm just going to steal all that. Copy, paste. I need to make that extra straggler there go away. Yeah. Actually, I need to move it a little further down, don't I? Yeah, I do. Let's do that. So I'll make that straggler go away. And I'll move my equal sign down. Much better. All right, so doing my glorified digital blackboard math. I'm going to make this line go away and just put in what the pieces are. That'll be f of r, 0, 0. Yay! So when we plow the field, we're only going to get two non-zero terms. So we're going to get a 1 over r squared sine theta. And let's see, we plowed this, we get 0. We plowed that, we get 0. So nothing in the r hat. Or I should say two potentially non-zero terms. Terms that aren't explicitly 0. So we go look at the theta hat. That's potentially non-zero, although it's 0. That is clearly 0. So we have a theta hat r partial phi of f of r minus, it'll turn out, when we do this, this gives me 0, but that is negative. So minus phi hat r sine phi partial theta of f of r. All right, but this depends on r, and we're differentiating with respect to phi, so that's 0. This depends on r, we're differentiating with respect to phi, so that's 0. So we can kiss both of those terms goodbye. And so sure enough, we end up with the curl of f is the null vector. So any central force is conservative. All right. So we can follow that thought through and just get the potential energy if we wanted to. So let's do that. So the potential energy we showed earlier, this would be equal to negative of the integral from our reference radius to r f dot dr. This will be little f times r hat. Then for the f, and then our dr we've done before, that's going to be dr r hat. So you end up with minus integral r ref to r of f of r dr. Okay. So we can go ahead and formally differentiate that and get that our f of r is minus dv dr, which is what we had before, but just to show that it ties in both directions. Okay, so it's probably worth now turning our attention to the, we've already done the differential equation of the orbit. Now it's time to do the energy equation of the orbit. So this is the energy equation of the orbit. And again, we'll do it for a central field. All right. So we recall in polar coordinates, we could write the velocity of something as r dot r hat plus r theta dot theta hat. And we could say that v squared is equal to v dot v. So that'll be r dot squared plus r squared theta dot squared. All right. Well, remember that the total mechanical energy has to be a constant. So T will be 1/2 mv squared, which we just worked out as r dot squared plus r squared theta dot squared. This will have to be plus rv of r, and that has to equal our constant E. We'll do the same trick we've usually done. We'll let u equal 1 over r, and that gave us, if you recall, that r dot was minus L du d theta, and theta dot was equal to Lu squared. So putting in here, this becomes 1/2 m L squared, so that will be du d theta squared plus u to the negative 2 L squared u to the 4 for that bit there. Plus rv of u to the negative 1, that has to equal our constant E. All right, we can clean this up just a little bit. There's an L squared everywhere in here. So we write this at least as 1/2 mL squared times du d theta squared. So this isn't the second derivative, it's the first derivative squared, plus u squared, after we do the cancellations there, plus rv of u to the negative 1 equals the total mechanical energy. So that is the energy equation of the orbit. So let's revisit from the previous video our friend the logarithmic spiral. Remember, we worked out that it has a inverse cube law as the force. So we had that r was equal to k e to the alpha theta. So that means our u is k to the negative 1 e to the minus alpha theta. So du d theta would be, differentiate that, we'll get a minus k to the minus 1 alpha e to the minus alpha theta. All right, so putting that in, our energy equation of the orbit now becomes, we have 1/2 mL squared. And so then we've got that derivative, that du d theta squared. So we'll have to square what we just found and put it in. So we get a plus k to the negative 2 alpha squared e to the minus 2 alpha theta. And then we put in u squared itself. So plus k to the negative 2 e to the minus 2 alpha theta plus v of u to the negative 1 equals E. All right, now if we look at this, if we start rewriting it back in terms of r, now that we're convenient again, this much of it we can look at here and say, oh, hey, that's just alpha squared over r squared. And this much here, we can just look and say, oh, hey, that's just plain 1 over r squared. So it's like before. So now I have a 1/2 mL squared. I can pull out a 1 over r squared, and I am left with, whoops, not an a, alpha squared plus 1. Yeah, I guess I don't really need the square bracket now, do I? There. much better. So alpha squared plus 1 plus v of r equals our E. So we can get our potential is our constant E, whatever it is, we just know it's a constant, minus 1/2 ml squared over r alpha squared plus 1. So our force will be equal to the negative gradient of V. So again, remembering our rules for the gradient, if we go back far enough, gradient, in spherical coordinates, since we only have a function of r here, we're just going to have the r hat dr, and the other parts don't matter. So going back, this becomes minus r hat partial r of our E minus 1/2 ml squared over r alpha squared plus 1. All right, so oops. Sorry, I think I dropped a term somewhere. Oops, that should have been over r squared there. I knew I dropped something. Okay. So we go ahead and take the derivative with respect to E is just 0. Minus minus is a plus, but don't get too excited because this will become minus minus 2, right? R to the negative 3. Yeah. So we're going to end up with minus what we had before, ml squared alpha squared plus 1 over r cubed r hat. No, wait, no. What was I doing there? Yeah, that's what we had before. All right. But again, we got a lot easier. Similarly, now we can go ahead and start to tackle the orbital energies. So our potential V of r is equal to minus k over r. So sorry, this is for a inverse square field. My bad. So we can write that as minus ku. So we're just doing what we did before. All right, so we can go ahead and write the energy equation of the orbit. So we'll have 1/2 ml squared there we go, du d theta squared plus u squared, and our potential is minus ku equals a constant E. All right, so we can rearrange this a bit. 1/2 ml squared du d theta squared equals E plus ku minus 1/2 ml squared u, right? Yeah, squared. All right, I can divide through by 1/2 ml squared everywhere and then take the square root. So I get that du d theta equals the square root of 2e over ml squared plus 2k over ml squared u minus u squared. All right. So we can rearrange this here, and we can separate the variables. This is separable at least. Okay, d theta equals, whew, that was the hard bit, du over the square root of 2e over ml squared plus 2k over ml squared u minus u squared. Really has to say, oh, hey, you know what? This is a quadratic, right? So, okay, I've got it written backwards, so this would be a u squared, b, and then that's c. So we're just going to go ahead and identify that accordingly. A is equal to -1. That stuff there is b. That stuff there is c. Just to make this a little easier to write. All right, so integrating the left-hand side just gives me some theta minus theta naught. Right-hand side a little trickier. Integral du over root au squared plus bu plus c. But yay, I looked it up. This will be equal to 1 over the square root of minus a, but keep in mind a is negative, so the answer so far is real. Yay. Inverse cosine of b plus 2au over root b squared minus 4ac. All right, so I can rearrange a bit. So I can say that minus b plus 2au over the root is equal to the cosine of root minus a times my theta minus theta naught. All right. And that will give me minus b plus 2au equals the root times the cosine, like so. Eventually we'll isolate u. U will equal the square root over minus 2a times the cosine plus b over minus 2a. All right. So putting in for what we have, this is just the cosine of the root here is just 1, thank God. So we can put in that 1 over r is equal to the root of. Now we'll start substituting in. We're going to get a 4k squared over m squared L to the 4 plus 4 times 2e over ml squared. That's over 2 because a is -1 times the cosine is just theta minus theta naught because root negative a is just 1 plus k over ml squared. We can eventually invert this, so you get that r is equal to ml squared over k over 1 plus the root 1 plus 2e ml squared over k squared times the cosine of theta minus theta naught. All right, now the important thing to recognize here is, well, actually, I'm going to put it to you. What is this? What should this look like the equation of? Pause it and we'll get back to you. All right, this should look to you like the equation of an ellipse. Thank God. That's why we were fighting so hard to get here. Remember, it's equal to the lattice rectum over 1 plus the eccentricity, cosine theta. So that minus theta naught's just defining the defining where the semi-major axis lies in the plane. So we can identify the eccentricity of the ellipse as being root 1 plus 2 EML squared over k squared. Now our lattice rectum, remember, is also equal to the semi-major axis times 1 minus the square of the eccentricity. And we identify that the lattice rectum is ml squared over k. All right, so grinding through, this works out to be a times 1 minus 1 plus 2EML squared over k squared. Just putting in what we identified for the eccentricity already and squaring it. That's equal to ml squared over k. The ones kill each other, so that's something. So we're left with a minus sign here, so we can't forget that. And then otherwise, let's see, we can cancel these m's, we can cancel the L squareds, we can cancel 1 power of k. So we can rewrite this as the energy is minus k over 2a. Now you've done this before in intro physics for the situation where it's a circular orbit and you had a minus k over 2r, and it was a lot easier to get to. This turns out to be the usual rule of thumb. You can kind of solve it for the circle and then put in the semi-major axis where you have the radius, and usually you can get away with it. But doing it right for the general case is usually much more tedious. Now, I want to point something out here. Technically, this guy here isn't just the equation of an ellipse. It's actually the equation of a conic section in general. So we have lots of possibilities. So, of course, this involves me hopefully successfully drawing in 3D. There we go. So if I take a horizontal cross section, I'll get a circle. Eccentricity is 0. If I cut it at just some arbitrary angle, we'll have an eccentricity that's less than 1. We have an ellipse. You could say the circle is a special case of an ellipse. If I cut it parallel to the opposite face, this eccentricity of 1, that's a parabola. And if I cut it vertically, I'll have an eccentricity greater than 1, and that's a hyperbola. So look at what we've got here. So the eccentricity goes as the energy. So if the energy is negative, the eccentricity is less than 1. So we have either possibly a circle, more likely an ellipse. In any event, it's a closed orbit of some sort. If the energy is equal to 0, then that will give us an eccentricity of exactly 1. That will give us a parabola. And if our total orbital energy is greater than 0, then the eccentricity is greater than 1, we get a hyperbola. So this is a new prediction from universal gravitation. Remember, it just went so far as trying to fit Kepler's data and give us a good model of the force that would be doing that. And so this is based purely on closed orbits, and we've now made predictions for unbound orbits. And in fact, it turns out that many of the comets that fly past us are one-shot wonders. Some are parabolas and some are hyperbolas. Okay, in the next video, we're going to take a look at the case of what if our orbit is almost a circle. And then we'll also take a look at the end, what if our force is repulsive and we get some scattering.